Today, our video is going to be focusing on the alternative to physics practical as we look at the rectangular glass block and the interaction of light waves with it. Now, it's going to be an alternative to physics practical. So the experiment had been done, the reading had been taken. We are going to measure out the readings, tabulate our graph, answer the questions on the slope, look at the precautions we are going to take, and also answer some simple questions. Our work is cut out for us, but before we proceed, if you are here to subscribe, just take a minute, go ahead, subscribe to the channel so that you can have access to all of our video resources that will help you build academic excellence as we study together. So with that, let's head over to our video for today. So here's our question. We're told that the experiment set illustrates a practical demonstration carried out in the lab. The point QRST are outlines of the rectangular glass block as shown in the diagram being noted in red. A normal, a line that is at a right angle, is drawn at the point A, which is 2 centimeters from Q. So that means if you want to measure on our glass block, this will be 2 centimeters and it will meet ST at point B. A straight line DA was drawn such that angle DN is 30 degrees. Okay. Then 2 pins P1 and P2 were fixed vertically on the line DA. So this is the line DA. And we're going to have 2 pins P1 and P2. They are pinned there. So here we're going to put the first pin, that's P1, and here we're going to put another pin, that's P2. So when those pins are located on the straight line, inclined at an angle to the normal, and we are going to look at the other end of the rectangular glass block, we are going to see the image of those 2 pins, and the aim is that another pin P3 and P4 will be noted on the paper on which we place the rectangular glass block in such a way that everything will appear as if they are in a straight line. So that straight line will also join as shown in red to meet the outline of the glass block, and then we can take the measurements that will be asked to take from the experiment. So this is exactly what we are going to do. Now, from our resulting diagram, we can note the line AC, the line AB, the line BC, but we just need to know that from our diagram, this is already forming a right angle triangle, all right? From that right angle triangle, we can note the line AC, we can note the line BC, and we can also note the line AB. But if you are to take an angle from this particular diagram, we can see that here, the area being shaded in red, in the diagram that was called angle theta, but for us, we are noting that in the question, we are to note mu to be line BC over line AC. So line BC over AC, if you recollect our trigonometry from SOHCAHTOA, BC over AC, if you take this angle to be, let's say, alpha, okay, we can see that that is corresponding to sine, so that we have sine alpha is opposite over hypotenuse, and the opposite in this diagram is the line BC, that's opposite to the alpha that we are noting, okay? So that means mu is sine alpha, all right? That's BC over AC. That's just the geometry of what we are being asked to observe and take the reading of. So we have to get that BC, we have to get the AC, we have to evaluate cos theta, and then we repeat the procedure for other values of I. Initially, we are starting with 30. We are also going to take some other values for I. So now, noting that what we now need to go is we can proceed with the practical question. Here we are told that there is a figure 2A that is showing the values. So let's see figure 2A. This is figure 2A, and this is where we are going to be taking our measurement. We are told that it will be showing the values of line AC, line BC, and theta for 5 different cases, okay? So from that measurement, from that diagram, we'll measure and record the values. So that means here, we are going to measure, look at the diagram, we have AB, that's going to be constant, but AC, now we have our angle here, the incident angle, we have it there, but then we'll note that AC is going to be changing because we have AC1, AC2, AC3. So we'll measure and record the values. We'll get AC, BC, and theta. We'll evaluate mu is BC over AC. We'll tabulate our readings. Then, interestingly, in our practicals, we are going to plot the graph. We are going to plot here. We are told that cos theta will be on the vertical axis, okay? And then mu will be on the horizontal axis. And recall mu is sine alpha. So the graph is, well, let's assume that we don't know. Is either going to be a positive straight line or it's going to be a negative straight line. But let's assume that it's going to be a positive straight line like this. So we have to plot that graph. We are also to determine the slope of the graph. So for this question, the slope will be change in the vertical axis, which is cos theta, over change in the horizontal axis, which is mu. So our slope we can get as change in cos theta over change in mu. Then, after determining that, we can state the precautions that are necessary to ensure accurate results when performing the experiment. So our work is cut out for us. Let's go and take our readings. Here, if you recollect, we are told that this length to the point where the number is drawn is 2 centimeters. So we can verify with our ruler. Okay, so exactly this is 2 centimeters. So we are actually having a roughly correct diagram, even though it's looking skewed because of the scan, but we know that is 2 centimeters. So we can see AB is 6.2 centimeters, but we are not asked to actually find AB. We're asked to find AC, and we're asked to find BC. Okay, and just noting that AB is 6.2 centimeters. So we want to get AC, BC, and theta. Now, taking the value AC1, because AC will be taken concurrently, we can see this is 6.4 centimeters. Okay, so AC2 in the second case, that will be 6.7 centimeters, and on like that. We are going to take that reading. I will speed up my video so that we won't just get bored with repeating the same thing over and over again. So after taking the values of AC, we are now going to BC, and in the same value, we are going to also take, now from B to C1, these are the points that are notched off. We just take off the reading and note them appropriately, like BC1, if we center the ruler correctly, that will be 1.6 centimeters. And we just mark up the reading and take it appropriately also. So now, moving on from there, we want to take our protractor and measure the angle theta in each respective case. Okay, so first, theta 1, we put the center of the protractor at the point of intersection of the line on C1, just as being shown in red, and we'll measure up that theta 1. From this diagram, theta 1 will be 72 degrees. We do the same for theta 2, theta 3, 4, and 5. And with that, we will get our table of values. So now, after getting our table of values, what I'm going to do is I'm going to take it to our worksheet beside the graph paper, and we're going to complete the table by evaluating the other values that we're asked to include in our table of values. Now we have our table of values, and if you are noticing something, I'm putting the unit of all the measurements. You also want to do that. When you have AC, put the unit in centimeters, theta in degrees. Then for mu, we now have BC over AC. That's 1.6 divided by 6.4, and that is 0.25. Now, because I'm going to be having decimal places, it's ideal that you use as much decimal places as possible. If you are plotting your graph, you can approximate, but on the table of values, please include those values as much as you can. I'm choosing to use 4 decimal places. So in the first case, I'm also having cos theta, that's cos 72, and that is 0.3090. You can see I'm using 4 decimal places, and I'm going to repeat this for all the entries. So next we have 2.7 over 6.8, that's 0.3971. I'm approximating the last decimal place, okay? Then cos theta, that's cos 53, 0.6018. And I will repeat the same step for the subsequent value. So I'm going to speed up my video again, but you can see the process as it's being done. This is the right thing to do. You write it legibly. You make sure that you put as much decimal places as appropriate so that your marks are not deducted. So now that our table of values have been gotten, we can bring in our graph. And first and foremost, we want to see how are we going to scale this graph appropriately. Now we are to plot mu against cos theta. Okay, mu will be on the x-axis, cos theta will be on the y-axis. What are the values that we need to represent? On the s-axis, we are seeing that the least value is 0.25. We can say 0.2, and the largest value is 0.6026. On the y-axis, we have 0.3 to 0.92. So these are the values that we want to scale. But we need to note something. 0 is not included in either of these values, either for mu or cos theta. So we don't need the origin. It's not compulsory you start with the origin. In short, when you have values like this, it's better not to start from origin so that your graph can be very bold, it can be very clear. On the graph, we are saying we are not starting with the origin, so we can notch like this to show that we are not starting from the origin. Then we need to put the values and scale appropriately. Here, let me take the x-axis. I'm having 0.3 to 0.92. And with this number of divisions, if I'm saying this is 0.2 and I'm leaving two boxes, two big boxes as shown, I can see that I have 0.2 to 0.6 already, which already is covering the scope of what I want to use. That means if I want to scale that, I'm going to use 2 centimeters to represent 0.05 units. Now, moving on to the cos theta axis, I want to have the least value to be 0.2, okay? But if in this particular case, if I scale in a difference of 0.1, I have 0.2, 0.3, 0.4, I can see that that will cover the scope of what I want to put on the graph. I have 0.2, I have 1.0. That is also covering my values on the cos theta axis. So already I have my scale. So now my scale is quite out. I will just note that on the mu, which is the horizontal axis, I'm using 2 centimeters to represent 0.05 units on the mu axis. Okay, so that's 0.05 units. And then on the cos theta axis, I'm using 2 centimeters to represent 0.1 units on the cos theta axis. So with this, already I know that my scale is up. I can label my graph and my table. This is a graph of mu against cos theta. Okay. If you notice, cos theta is a ratio, so it's not having any unit. Mu is also a ratio, it's also not having any unit, so I leave them unitless. If there is a unit, it's appropriate that you also put the unit. So that's our label for the graph, that's our label for the table of values. Then we can go ahead to plot subsequent entries against one another. Like on the horizontal axis, we have 0.25. That will be between 0.2 and 0.3. So this is 0.25 being shown in blue. Then on cos theta, we have 0.3090. 3090 will be approximately 0.31. Okay. Now we have, with this scale, each of the small boxes will be 0.02. So 0.309 or 0.31 will be in between 0.3 and the next small box. Okay. So I can just say is here and I can join to the value of mu on the horizontal axis. I'm not going to be showing that again. I'll just show the point of intersection. Okay. So if I'm showing the point of intersection, I will just do the same for all the subsequent entries. We have 0.3971 and 0.6018. You can plot them together like that and locate them. I will also speed up the video now so that I just note the point of intersection. So now with all the points located, I want to find the line of best fit. That is the line that is best describing all these values together. I don't want too many to be on the left. I don't want too many to be on the right. As much as possible, I want a line that can pass through as many points as possible, or it can be a centralized line passing through the midst of all these scatter plots. Okay, so that's why I'm doing that on the graph. I'm just looking at, with your ruler, you can gauge it and see, is this one better? Is this one not better than what I'm trying to put? And you get your line. For me, I think this will be quite good. I can see it's like wanting to pass through the origin. So I can just draw my line from the origin and take it to the top just like this. And with that, I've drawn my graph as requested in the question. Okay, so that's a graph of mu against cos theta. So after doing this now, what we're asked, if you still recollect, is that we have to find the slope of the graph. Okay, now we have to find the slope of the graph, and as identified initially, the slope is a change in the vertical axis over the change in the horizontal axis. So we can define that our slope is change in cos theta over change in mu. That means we are going to take 2 points along the line of the graph. We are going to look at the components on the vertical axis. We are going to look at the components on the horizontal axis. So now we are going to get those 2 points. For me, I like taking points that are easy to read. So I can take my first point there at the base and look at some other points where I can pick the second. I think here will also be okay for me. So I can draw like a triangle just for me to get the change in values on the horizontal and the vertical axis. Okay, now this will be change in cos theta and this will be change in mu. So if I trace to the component on the vertical axis, I can see that that point at the uppermost part is corresponding to 0.85, okay, and the one at the lower side is 0.2. So I can get my change in cos theta already. That will be 0.85 minus 0.2. So my slope will be, change in cos theta will be 0.85 minus 0.2 divided by, now the change in mu, the value for mu here is 0.55 and 0.20, okay? So I have 0.55 minus 0.20. Okay, it's coincidental that 0.20 is the value for both the lower values in this case. So if you are to subtract and divide, we are going to have 0.65 divided by 0.35. So that will be 1.857142. So that will give us 1.857. That is the value for the slope of our graph. So with this, we can now move on to the other question that we have asked in the question. We are asked to state the precautions that we can take when performing this experiment. And now I've listed them out here. And number one I want to talk about is that parallax error was avoided in the protractor or the meter rule. That means while taking the measurement with the measuring instrument, either the meter rule or the protractor, the angle of view on the instrument was held directly and it was not angled. If it was angled, because they are plastic, that will refract our reading so that we may get a little bit wrong value to take for our value. But to avoid that, we need to look directly on top of the measuring instrument so that we can take our correct readings. Then if there is any zero error on the meter rule, that was also noted. For example, if the meter rule had broken and it's not starting from 0, then we need to note, okay, it's starting from 1. So when I'm saying 7, that should be 6. All right. Then optical pins were maintained erect or upright while performing the experiment, meaning that the positioning of the pins was observed to be straight and not at any angle. If it is at any angle, if it is bending, we will not be able to get the alignment on the pins. So, and without getting that, that means that we are not getting an accurate rays of light coming from our pins. So if the glass block is here, we want to make sure that the pins, they are erect and not slanting or bending over. Then finally, there's reasonable space between the pins so that we're not just moving them too close together, but they are giving considerable amount of space to work with. Now, in our final question here, we're asked to define the principal axis of a concave mirror. And the principal axis is an imaginary line joining the center of curvature through the principal focus to the pole. So if you want to denote that in the diagram, let's say this is our concave mirror, okay? Now there will be a line at the middle running through that mirror, and on that line, we are going to locate the principal focus and the pole or the center of curvature of the concave mirror. So if rays of light being shown in orange is coming like that, normally they will go to pass through the center of curvature, they will go to pass through the principal focus, but because it's a concave mirror, they'll be diverted back from where they are coming from. So that's the center of curvature, that's the principal focus, and the line joining them through the center of the mirror is the principal axis of the concave mirror. So in this particular case, it's the line being shown in blue. So this is the principal axis of the concave mirror. And that's solution number 1 in our solution to these further questions in the practical. And solution number 2, we are told that an object of height 2 cm is 6 cm in front of a concave mirror. We are to calculate the magnification and the distance of the image produced if the image height is 4.1 cm. We know that magnification can be defined as the height of the image over the height of the object, or the distance of the image from the mirror divided by the distance of the object to the mirror. So we have 2 formulas, even 3 formulas that we can use here. We can say M can be defined as V over U, that's image distance over object distance, or the height of the image divided by the height of the object. What we are giving the height of the object to be 2 cm. We are giving the distance of the object to be 6 cm. We are to find the magnification, and we're also to find the distance of the image. Okay. Now, the height of the image we are given to be 4.1 centimeters. Now, taking any of the formula, looking at our formula, we can say that the image height over the object height is equal to the image distance over the object distance. So if we substitute all these values, we will have 4.1 over 2 is equal to V over 6, so that V is 6 times 4.1 over 2. If we cut, that will be 3 times 4.1, and that will be 12.3 centimeters. So the image distance is 12.3 centimeters. The magnification, we can say it is the image distance over object distance, or image height over object height. And we have to take the image distance over the object distance, we can say that is 12.3 over 6, and that will be 2.05. It is unitless, it's not carrying any unit. And with that, we have been able to cover this experiment on optics, talking about the rectangular glass block, in which we have looked at the properties of light rays as they are being refracted through a rectangular glass block. I hope this video has been informative, useful, and I hope it will help you prepare better for your exam, particularly if you are doing your WAEC, your O-level, your NECO, your GCE exam. I hope you'll find this useful. So that's all we are going to be having in our lecture today. We hope that this will be of benefit, of use to somebody out there. Don't forget to subscribe to our channel. We have a lot of resources that you can use to enhance your academic excellence. And that's our desire, that you go out and be the best. And as you do all this, we know that all will work out together for good. Until next time, God bless you.